Today we're going to start Unit 2A, which is about chemical counting. What we're going to look at today will be some general information about how scientists handle numbers, what numbers mean in science, something about a number system, a number notating system that we use for very large numbers and very small numbers, which are important in chemistry very often. And then we're also going to look at a particular unit that we use for really large numbers of particles, which also happens a lot in chemistry. And then we're going to look at ratios. Some of this makes real good common sense when you think about what we know about how compounds are put together. Data is information that's based on measurements. Data is made up of two parts, not just numbers, although that's part of it. Quantity. Quantity answers two questions. One of the questions is how much or how many. Those are the questions that are answered by the quantity. So this is numbers like 5 or 10 or 35.6. Those are all quantities, but they don't really mean anything without a unit. And a unit completes the information by answering the question of what? How much or how many of what? So 5 miles tells you what that number means. 10 pounds tells you what that number means. 35.6 liters tells you something more information. It makes it not just a number, but a meaningful number that comes from real life. And that's the kind of information that we work with numerically in science. All of our numbers have a unit attached to them unless they turn out to be a ratio of some kind. In chemical compounds, we've already seen that there are fixed ratios of atoms of one element to another. For example, in water, we've seen that there are 2 atoms of H for every 1 molecule of water. We've also seen that there's 1 atom of oxygen for every 1 molecule of water. We've also seen that means that there is one atom of O for every 2 atoms of H in water. We could also say the same thing for carbon dioxide. CO2, the ratios there are 1 atom of C for every 1 molecule of CO2, or we could say 2 atoms of O for every 1 molecule of CO2, or we could say 2 atoms O for every 1 atom of C. All those things are true. The ratios are the same no matter how big the sample is. A bigger sample just means more molecules. So while there are 2 atoms of H for every 1 molecule of O, there would be 2 million atoms of H for every 1 million molecules, or 1 million atoms of O for every 1 million molecules of H2O. Bigger sample just means more molecules. In any reasonable sized sample of an actual substance, there will be a huge number of molecules because molecules are so tiny. For example, a drop of water, here is how many molecules of water are present. That's a huge number. Those kinds of numbers are used all the time in chemistry if you're counting actual teeny tiny particles like atoms, ions, or molecules. And so we need a way to deal with these really big numbers. We also need a way to deal with really small numbers if we're measuring things as tiny as ions, molecules, or atoms. So we make use of this tool called scientific notation. Some of you will have some familiarity with scientific notation because of the fact that you've used it in math classes before, or something like it in math classes. Scientific notation is based on this idea. Every number that there is can be written in the form m times 10 raised to the n power. M has a name. It's called the mantissa. And in scientific notation, the mantissa has a range. It's going to have to be greater than or equal to 1, but it has to be less than 10. So somewhere in this range of 1 up to 9.999 something, that's what the mantissa has to fall into. That's the m part of the number. The exponent is what n is called, or sometimes it's called the order of magnitude. It's a positive or negative whole number. So n is a whole number. It could be plus or minus. If n is greater than 0, that means that the number you're describing is a number that's bigger than 10. If n is less than 0, then that means the number you're describing is less than 1, so it's a decimal. If n equals 0, well, then that means you have a number that's between 1 and 10. Here's this number that's the number of molecules of water in a droplet of water. Here's how I can write this in scientific notation. First of all, I want a mantissa that is between 1 and 10. I'm going to do that by finding where the decimal point is located. Here it's not really there, it's an implied decimal point. And I'm going to move it however many spaces I have to until I have a number that's between 1 and 10. So I'll move it to the left, 3, 6, 9, 12, 15, 18, 21 places. And then I have 1.3, a number between 1 and 10. So you're going to move it as many places as you have to until you have one number exactly, one digit exactly to its left. So that's going to be my mantissa, the 1.3 part. And then what's my exponent? Well, I moved it 21 places, and it's a number that's bigger than 10, so that means I'm going to have a positive exponent, so my order of magnitude is 21. So 1.3 times 10 to the 21 is that number. It's a lot easier to write, and we're going to find out later it's easier to do calculations with. I want to show you a little trick here, not trick, but a technique. To put a number like this into your graphing calculator, here's what you want to do. Instead of doing 1.3 and then times and then 10 and then a hat and then 21, which is going to screw you up sometimes because of orders of operations when you start using these numbers in actual problems, don't do it that way. This is a way to enter this in your calculator that's built into how your graphing calculators work. And if you don't have a graphing calculator, if you have a regular scientific calculator, you can watch a little video on our class website that will show you how to handle several other kinds of calculators. So 1.3, and then second button, and then comma. Up above the comma you see a EE. That EE button stands somehow for exponential notation. I'm not sure why it's two E's. You see an E show up in the display. That E means times 10 to the whatever comes next. So then I would key in 21. So 1.3 E21 is really 1.3 times 10 to the 21. Now your calculator doesn't recognize this as a multiplication problem like it did the other example that I put up here earlier. This is recognized by your calculator as one number. And that's good because if I'm going to divide that by another number, 1.3 times 10 to the 20th, for example, I'll get a better answer. My answer, if I had done it with the times and the 10 and the hat key and the 21, would have been a different number and it would have been wrong. So get in the habit of using second function E to raise something to a power. Well, for convenience, chemists have a number that they use to count out atoms or molecules, small particles. Ions even would fall into this category. Sort of like if you're counting donuts, if you work at the bakery, you count them by the dozen. So, and eggs. Eggs, we sell eggs by the dozen. So this is like a number that's a standard unit, like a dozen, except it's a way bigger number. It's called a mole. It's a chemical counting number. Mole is abbreviated MOL. It's not much of an abbreviation. A mole is approximately equal to 6.022 times 10 to the 23rd items. So it's a number that's way bigger than a dozen, but it's a number that's consistent. A mole of anything is 6.022 times 10 to the 23rd of that thing. That number is a name, too. It's called Avogadro's number. It's named after Amadeo Avogadro, who was someone who did a lot of studies early on that pointed toward the direction of small particles like atoms. Well, since a mole is a consistently sized number, then those big ratios that we had, like 1,000,000 atoms to 2,000,000 atoms or something like that, well, that will also apply to moles. So any ratio of particles is also the ratio of moles. So, for example, we could say for water, 6.022 times 10 to the 23rd atoms of O go with 6.022 times 10 to the 23rd molecules of water. This is the same as saying 1 mole of oxygen atoms goes to 1 mole of H2O molecules. It's the same ratio. These ratios have a descriptive but not very creative name. They're called mole ratios. They're extremely important in chemistry. We use them to make calculations and predictions all the time. We'll learn more about that later on. We looked at molecules and we were laying out this idea of a mole ratio. But for an ionic compound, there are no molecules. There are just ratios of ions. The smallest whole number ratio of these ions in an ionic compound is what we call a formula unit. And a formula unit is sort of like a substitute for a molecule. It's sort of the ionic version of a molecule. It's just the smallest ratio that there is. We can treat it like a molecule in making up these ratios. For example, with the ionic compound NaCl, we could say 1 atom of Na corresponds to 1 formula unit of NaCl, but we could also say 1 mole of Na atoms corresponds to 1 mole of NaCl formula units.